Today's lesson involves more solving problems with sinusoidal functions, but we're adding the modeling piece to it, the coming up with the equation for the situation. So our goal is to model and solve a variety of problems involving sinusoidal functions. Our first example is a Ferris wheel example, and it has a diameter of 20 meters. It's 4 meters above the ground at its lowest point. Assume that the rider is located 30 degrees from the lowest point and is heading towards the lowest point when the rider started to be tracked. Write an equation to model the rider's height above the ground versus the angle using a transformed sinusoidal function. Well, sine function specifically, it's asking for sine as opposed to cosine. So let's take into consideration what we have here. We know that the diameter of the wheel, and I'm just going to draw that Ferris wheel here. Okay, so there's the center of the wheel. The diameter then is all the way across. That's 20 meters. And we have a height of 4 meters above the ground level. So we'll make this 4 meters here, 24 to a maximum height here. Let's see what we can get from there. So our diameter is 20, which means the radius of the wheel is 10. That gives us our amplitude for our function. So our radius is 10, so this would be 10 and 10. And those are meters. That makes the axle of the wheel 14 meters up. So the equation for the axis of the curve will be y equals 14. Our amplitude will equal the radius of our wheel, which is 10, because we're oscillating between a high of 24 down to a low of 4. What else do we need to know? We need to get a K value. Now this one actually is being tracked versus the angle that the wheel has rotated. So our period is just the 360 degrees. Our K value is just 1. So we don't have to worry about putting a K in, but we do have the fact that the person is 30 degrees from the lowest point, depending on which way we're looking at this. This angle in here could be 30 degrees, the central angle, that's what that's called, and we're going to come up with circle angle stuff in our next unit, so that's a highlight to that. And we're heading towards the lowest point, so this way. So if I were to actually sketch this function, the person is not quite at their lowest height, but at the 30 degrees in to the ride, they would be at the lowest point, and then they would head back up and come back down and so on. Okay, so we're looking like a function something like that. 60 degrees prior to that, we would have been on the axis of the curve. So at negative 30, so that's 60 degrees, negative 60 degrees, we should be on the axis of the curve there. So those are 90 degrees apart, that makes sense. So now we're going to come up with our equation, and with these we should be putting let statements in there, so we could let H represent the height of the rider in meters. So I will be looking for these let statements for communication on your assessments. So let H represent the height of the rider in meters, and make sure you include your units with your let statements. And I'm going to let theta, or you could let x, whichever makes you smile, pick one, represent the angle the wheel has rotated. That's supposed to say has rotated. Okay, and then we could write H at theta, height at angle theta. I'm actually going to, now this, my graph here is definitely not drawn to scale. I know that 90 degrees after, okay, so my diagram graph is not drawn to scale here. Each one of the anchor points, though, should be 90 degrees apart because we're 90 degrees for a quarter rotation of a turn here. All right, amplitude is 10. We're going to go with sine. K is just 1. We're going to have theta, but it does have a phase shift to it, so we're going to go 120 degrees based on my sketch of the curve. 120 degrees to the right. I could do a negative in front of that 10 and then go 60 to the left. That would also work. And then we have a plus 14 for our axis of the curve. Now, at what angles is the rider's height? 16 meters above the ground. So 16 goes in for our height, and we're going to just solve that equation like we had done yesterday or in the previous lesson to get our theta by itself. I'm going to subtract 14 from both sides. So 16 take away 14 gives me a 2 here. And then we are going to divide both sides by 10. So that's going to give me 0.2 and leaves me with sine of theta minus 120 degrees. And then inverse function of sine on the point 2, and I get 11.54 roughly. And that's going to equal theta minus 120. And then I'm going to add 120 to both sides, and that gives me 131.5 as my answer there. Whoa, 131.5. I don't know whether you saw that. The whole screen just flashed and I thought I had lost everything. It was kind of weird on my end, but all right, so that's 131.5 degrees and 16 meters. That is going to be above my axis of the curve. There should be a second answer to that, and when I find my second answer, it actually comes from the cast rule. We're at 11.54, but we're also going to be in that second quadrant. I'm going to do 180, subtract that 11.54, and we get 168.46 is equal to the theta minus 120, and then I'm going to add 120 to that, and we get 288.46, or about 288.5. Equals theta, and that's in degrees there. Oops. Okay, so hopefully that makes sense so far. All right, example number 2. The propeller of a small airplane has an overall length of 2 meters. The propeller clears the ground by a distance of 40, that should say 40 centimeters, not 40 meters. So I have a typo there. That should be 40 centimeters. And spins at 1200 revolutions per minute while the airplane is taxiing. The tip of the propeller is at its maximum when its height is started to be tracked. Okay, so you've got the propeller on the end of the plane. I'm not going to be very good at drawing this, but I'll try my best. So let's make a little propeller here. It's supposed to be the propeller on the end of the nose of the plane there. So we've got the ground. We've got 40 centimeters being the distance that the propeller is going to clear the ground by. And then the propeller itself has an overall length of 2 meters. So the 2 meters was intended to be from top to bottom, assuming that like these are kind of connected. So 2 meters there, or 200 centimeters. It depends which unit you're going to use. You have to define that. And it's spinning. Okay, it's spinning at revolutions. So for one period, we're really looking at how long, the time it takes that propeller to make one full turn. So we need the time per is divide 1 revolution. That's what we need to get. 1 revolution. So the dividing piece there. So our time, it was per minute, so 60 seconds. I'm going to change this into seconds. That would be 1200 revolutions. So it's 60 seconds per 1200. I'm going to actually do the dividing here, and I get 0.05. So that's how many seconds. It's like, whew, not very much time at all. Well, and it shouldn't be because it's a plane and it's got to move fast. Seconds per revolution. Now, that is the period. To get the k value, we have to take 360 and divide it by the period. Okay, so 360 divided by 0.05, that gives us 7,200 here. That's going to be my k value in my equation. Now the amplitude, we've got a diameter here of 2 meters. The amplitude would equal the radius. The amplitude, or a value, is going to be 1 meter. The axis, the middle point of that rotating propeller, would be 1.4 meters above the ground. So we have the axis of the curve at 1.4. What else do we need? The tip of the propeller is at its maximum when the height is starting to be tracked. So height is up at the 2.4 meters above the ground, comes down and goes back up again. So because it's starting at the maximum, I think cosine is a good choice for this particular function. All right, again, we need let statements for this, which I'm going to type in, and then we'll create our equation. Okay, so height is in meters, I decided, and t is the time in seconds. You can do this problem in terms of centimeters as your height, centimeters above the ground. It's just you're going to have your a and your axis of the curve going to be multiples of 100 compared to mine. All right, so my a value is just a 1, so I'll just leave that out. I'm going to work with cosine because we're starting with the maximum. My k value is 7,200, and then we're going to have a t, and I don't need the brackets around the t, but I put them in there just because. And then we've got the 1.4. All right. Part B, determine all times in the first 2 cycles when the tip is 1 meters above the ground. Okay, so 1 meter above the ground, this is 0.4 at our lowest point. So I'm just looking at the graph here. 1 meter is going to be somewhere here because my axis of the curve would be at 1.4 meters. So we're going to have 2 times for that. Let's see what I can do with that. So I want to put in 1 for my height. We're going to have the cos of 7,200 t, and then plus 1.4. I'm going to subtract 1.4 from both sides. We're going to get negative 0.4 is equal to the cos of the 7,200 t. So we're going to go 0.4 negative, and I'm going to do inverse function cos on that, and I get 113.58, and this is just time, so I'm going to keep all those digits in my calculator, and then I'm going to divide that by 7,200 to get t by itself, and t is equal to 0.016 roughly, approximately that. Okay, cos is also negative in the third quadrant, so I could have this answer, or by cast, cos 113 would be here, 113.58, 113, we could have it also this way to here. Okay, so to get that answer, I'm just going to take 360 and subtract that 113.58. That's going to give me 246.42 roughly, equals 7,200 t. And then I'm going to divide by 7,200, and I get that t is also approximately equal to 0.034. Okay, so that's seconds and seconds. So that is during the first cycle. So that gives you your 0.1 here, your 0.3 here, sorry, 0.016 and 0.034. This is 0.05. To get my next 2 answers, I'm just adding the period to it, and the period we know is 0.05 because we calculated that earlier. So my other 2 times 0.05, it would be 0.084, and 0.066. And I would follow that up, of course, with a therefore statement.